Hi guys, today's lesson is on antiderivatives. This is lesson 38, so that you can download into your notes. Finding antiderivatives. For each of the following derivatives, find an original function called an antiderivative or indefinite integral. So in other words, I want to go backwards. We've been taking the derivative moving forwards, but I want to go in the opposite direction. So what would my original function, my f of x, be if my derivative is 2x? So before we had to take the exponent and move it down, now we're going to have to move it up. So I would start out with x squared, all right? And we're going to do the same for each of these. So in the second one, f of x is going to equal 1/2 x to the 2. And you can check all of these by actually taking the derivative of the one that you've just found and see that it gets back to the original. So you can hit pause and try to figure out the rest of these and then double check that you've done them correctly. In this third case, it would be 1/3 x to the 3. Then we have one way to look at this, f prime of x is x to the -2. That might help, so that you have negative x to the -1 or -1 over x. Again, rewriting the derivative as x to the -3 makes my original graph want to be x to the -2 divided by -2, or -1 over 2x squared. And then here with our cosine function, we want to remember cosine with the negatives in the middle. Remember that when we were using this strategy before, we were going down in this order because we were talking about a derivative. But now we're talking about antiderivatives, so we want to go in the opposite order and go up. Okay, so the derivative, or the integral of the cosine of x, the antiderivative, is going to be sine of x. All right. So in example 1, so it asks for all of these, what strategy did you use? Well, if you look at this, f1 of x, we had x cubed. f2 of x, we have x cubed minus 5. f3 of x, we have x cubed plus 97. If I were to take the integral of all of these and figure out what the original value is, I would say that my f of x is 3x squared. True? It works for all three. So how do I distinguish between them? Well, if f of x, don't know what happened there. If f of x is equal to x cubed plus c, that would be the antiderivative of f. That c, that constant, is going to make it true for each one of these cases. Okay? So over here, in general, we could say if y prime is equal to 2, I can say y is equal to 2x plus c. You want to have a constant for each and every time you do that. All right? So in general, if we're talking about mathematically what that looks like, it's theorem 4.1 in your textbook. If f is an antiderivative of little f on an interval I, then big G is an antiderivative of little f on the interval I, if and only if, IFF stands for if and only if, G is of the form g of x is equal to f of x plus c for all x in I where c is a constant. And if and only if means that it goes both forwards and backwards. It works both ways. So if I wanted to prove something like this, if g of x is equal to f of x plus c, f prime of x is equal to f of x, and c is a constant, then g prime of x is equal to the derivative of f of x plus c, which in fact gives me f prime of x plus 0, which we know to be f of x. So that proves what we've said above. Mathematically speaking, the notation, the antiderivative, also known as the integral, so y is equal to the integral of f of x dx is equal to capital F of x plus c. F of x dx is read as the antiderivative of f with respect to x. The differential dx serves to identify x as the variable of integration. And then the basic integration rules include that the integral of f prime of x dx is equal to f of x plus c. That plus c is so very important. You cannot forget that. Okay, that makes all the difference. Integration is the inverse of the differentiation. Okay, so that's that. At the top of this page are all sorts of integration formulas. You will need to know all of these, but the majority of these will come to you naturally. So if you're integrating 0, it's just going to be a constant. If you think about that, if you have a constant and you take the derivative of the constant, you get it 0. Remember, so you can always take the derivative of this side to get back to your integrand value and to check yourself. So if I took the derivative of kx, I would just get k. If I took the derivative, the plus c is a constant, it's just going to go away. If I have an integral value with a constant in front, we can simplify the integral by taking that constant and moving it to the front, just like we did when we derived. Likewise, with our integrals, we can actually separate them into separate integrals. This is the version of the power rule. So if I have the integral of x to the n, instead of when we did the derivative of x to the n, we would move the n to the front and add and subtract by 1. With integration, you actually take that power, you add 1, and you divide by whatever your new numerator, your new exponent is. And don't forget your plus c. N can never equal -1 in this case because we can't have it undefined. For all of these cases here, this is where you want to do cosine with the negatives in the middle, and you would end up going in the opposite direction for integration. Okay? We know that the derivative of the tangent is the secant squared. We know the derivative of the secant is the secant tan. We know the derivative of the negative cotangent is cosecant squared. And we know the derivative of negative cosecant is cosecant cotangent. So if you know them forwards, you'll be able to get to them backwards. But it's really important that you know them. Just like it's really important that you know your unit circle. Oh yeah, I went there. All right. In example 2, it says to describe the antiderivation of A, B, and C, and then rewrite them before integrating. So if I look at, for example, part A, if I'm going to rewrite it, I would rewrite it as x to the negative 3 dx. If I were to integrate it, I have that power rule where I can add 1 and divide by the numerator there. I mean the exponent, sorry, which just gives me x to the negative 2 over negative 2 plus c. And then to simplify that, that would just be negative 1 over 2x squared plus c. All right. In part B, I can rewrite it as x to the 1/2 dx. So that's going to be x to the 1/2 plus 1, which is 3/2, divided by 3/2, or multiplied by 2/3. So 2/3 x to the 3/2 plus c is my simplified version. And with the last one, I can take that 2 to the outside. I know cosine with the negatives in the middle, so the integral of sine is negative cosine, so I'm going to have negative 2 cosine of x plus c. Maybe it's best to show it how I got there. So I left the negative 2 in front. I found the integral to be, it was 2. I left the 2 in front. The integral of sine is cosine of x, and then plus c. So if I simplify it, it's negative 2 cosine of x plus c. All right? So for all of these, you can always check by differentiating. So you can differentiate your answer to see if you get to the original value. Okay? Let's try some more with example 3. In this case, this is the same thing as saying the integral of 1 dx. Well, the integral of 1 is just x plus c. Here, this is the same as saying the integral of x dx plus the integral of 2 dx, which in this case would be x squared over 2 plus c and 2x plus c. Notice I labeled my C1 and my C2 just differently so that I could see that I've done it, that I've added the constant for each one of these. But you can actually, in general, just combine these and rewrite it as a single constant. So your final answer can look something like this. All right, so in this case, C is equal to C1 plus C2. And that is always allowed. You don't see people usually writing them separately, so I just want to show you that out one time. And so likewise with this case, you don't have to write it out the long way. You can go right into it. For example, 3 is a constant. If I do my power rule, I have x to the 5 over 5 minus 5 is a constant. X to the 2 plus 1 is 3 over 3. And then for x, I'd have x squared over 2 plus c for all of them. This is the same thing as saying 3/5 x to the 5th minus 5/3 x to the 3 plus 1/2 x squared plus c. All right, it's all the same. Last page, example 4, hint, rewrite before integrating if necessary. So it is always beneficial to simplify your expression before integrating. In this case, I can rewrite this as a separate integral, as a separate fraction. So x over the square root of x plus 1 over the square root of x allows me to actually simplify that fraction a little bit as x to the 1/2 plus x to the negative 1/2, which makes it a lot easier when I go to do the power rule. This gives me x to the 3/2 over 3/2 plus x to the 1/2 over 1/2 plus c, and I can simplify that a bit. That should be a 2. X plus c. And if I wanted to, I could theoretically rewrite this like this. So again, making sure that you realize elements of your answer can be manipulated. That's definitely something that would reflect on the AP multiple choice part. In this second one, if I rewrite this as the integral of 1 over cosine of x times sine over cosine, it kind of allows me to see that we are dealing with, oh, well, what's 1 over cosine? Well, that's secant. And what's sine over cosine? That's tangent. And I know that the derivative of something is the secant tan. Oh, the derivative of the secant is secant tan. So secant of x, so the integral of secant tan is going to be secant plus c. So it's a lot easier sometimes if you simplify first before going on to the calculus part. So with initial conditions and particular solutions, the reason why we have the plus c and what it looks like in a graph is this. So if I integrate 3x squared minus 1, I get x cubed minus x plus c. This plus c is what is considered the general solution. A particular solution is when you're actually given what a specific point in the graph so that you could find a particular answer for that condition. So in general, y is equal to the integral of f of x dx. That has many solutions, each differing from the others by a constant, right? And then here, the graphs are all representing the antiderivatives as a vertical translation. So if you think about it, you have x cubed minus x plus c. If I do a plus 3, it's going to move it up 3. If I do a minus 2, it's going to move it down 2. So the graphs of any two antiderivatives of f are vertical translations of each other. Okay, and we'll go into this a bit more in the next few days. How can we determine a particular solution? So we need to know what y equals f of x is for one value of x. That's considered the initial condition. So for example, in the above figure, only one curve passes through the point 2, 4. If I want to find what that curve is, I have to start with my general solution. So to find the curve, I have f of x is equal to x cubed minus x plus c. This is considered the general solution. Then I'm given my initial condition. F of 2 is equal to 4. Initial condition. I'm going to plug in that initial condition. F of 2 is equal